This is the EdExcel A-Level Further Maths Paper 3 from the 2021 series, and in this video we will be taking a look at the Decision Mathematics 1 D1 paper. Question number 1. A Hamiltonian cycle for the graph in figure 1 begins C, V, E, X, A, W, etc. For part A, we have to complete the Hamiltonian cycle. Just as a reminder of the definition of a Hamiltonian cycle, it's one in which we visit every vertex exactly once. So, for part A, here is how our Hamiltonian cycle begins. We go from C to V. From V, we go to E. From E, we go to X. From X, we go to A. From A, we go to W. Now that we are at W, we can go to D, and then from D, we can go to Y, and now that we are at Y, we can go to B, now that we are at B, we can go to U, and now that we are at U, we need to go back to C, as seen over here. We have visited every vertex exactly once, returning to C. For part B of the question, hence use the planetary algorithm to determine whether the graph shown in figure 1 is planar. You must make your working clear and justify your answer. First of all, for part B, we form the Hamiltonian cycle. We've got C, V, E, X, A, W, D, Y, B, U, and then we go back to C. And then we join the other vertices. So if I start off with A is joined to U and V. So we need to join those up. A joins up with V. A would also join up with U. If we take a look at B, B is joined to V. So we join B with V. If we take a look at C, it's joined to V, and it's also joined to W, and it's also joined to X. So we've got CV, that's already shown. Then we have CX, and then we also have CW. If we take a look at D, that joins to W. It also joins to X, and it also joins to Y. So we have D joining to W. It joins up with X. It also joins up with Y. And if I take a look at E joins up with V, E also joins up with Y. So we join these up, as we see here. What we also know is E is joined to V and X. Our next step is to write out all of the edges inside of the Hamiltonian cycle. So we have AU, we also have AV, then we have BV, then we have CW, then we have CX, and then we have DX, and then we have EY. Now that we've done that, we can label one of these edges with I. Say we label AU with I. Let's show that AU has been labelled I, and then we see what crosses AU. Well, what you can see is BV crosses AU, so we have BV, which we label O. We also have CW, which crosses AU, so we label this with an O. We also have DX, which crosses AU, so we label DX with an O. And then we have EY, which crosses AU. So we label EY with an O. Now, what you will notice is the edges BV and CW intersect. And because those intersect, we can therefore conclude that the graph is not planar. So, because the graphs intersect here, we can conclude the graph is not planar. Question number 2. A project is modelled by the activity network shown in Figure 2. The activities are represented by the arcs. The number in brackets on each arc gives the time in hours to complete the corresponding activity. For part A, we have to complete diagram 1 in the answer book to show the early event times and the late event times. We begin at the source. We assign a value of 0 to it. For the early event time. Now, 0 plus the 4 is 4. That's the only thing going into here. So we put 4 over here. If we now take a look at the other values we can enter in, well, 4 plus the 2 is 6. And 4 plus the 4 is 8. And then we have 0 plus the 6, which is 6. So what goes into here, we compare the 8 with the 6, we choose the larger one. 8 goes into here. Now, we have 8 plus the 0 for the value for the dummy. That will be 8. We compared the 6 and the 8, we choose the larger one. 8 goes inside here. And then we have 8 plus the 5, which is 13. We also have the 0 plus the 10, which is 10. We choose the larger one. The 13 goes here. Now here we have 8 plus the 6, which is 14, or we have 8 plus the 7, which is 15. The larger one goes in, 15 goes here. Now, here we have 8 plus the 2, which is 10. We could also have the 13 plus the weight of the dummy, which is 0. Adding those together, we get 13. We choose the larger one. 13 goes here. Now, what goes inside here? We have the 13 plus the 5, which is 18. Nothing to compare it with. 18 goes here. And now in this final box we have 18 plus the weight of the dummy, which is 0. That gets us 18. We also have 15 plus the 7, which is 22. We also have 13 plus the 6, which is 19. And we also have 13 plus the 7, which is 20. The largest one is 22. So 22 goes here. We have now completed our forward passes. Let's now complete the backward passes. What goes here is 22. So 22 take away 0, that's 22. Nothing to compare it with, so 22 goes here. Now we have 22 take away the 6, that will be 16, nothing to compare it with, so 16 goes here. And then 22 take away 7, that's 15. Nothing to compare it with, so 15 would go here. Now, let's think about what could go here. We have 16 take away the 0, which is 16. We also have 22 take away 17, which is 15. We also have 22 take away 5, which is 17. The smallest one is 15. So 15 goes here. Now, what would go here? 15 take away 6. That's 9. Nothing else to compare it with. 9 goes here. And if we think about what could go here, we could have the 9 take away the 0, which is 9. 15 take away 7, that's 8. 16 take away 2, that's 14. 15 take away 5, that's 10. The smallest one is 8, so 8 goes here. Now, let's think about what could go here. 9 take away 2, that's 7. 8 take away 4, that's 4. We choose the smaller one, 4 goes here. Now, we have 4 take away 4, which is 0. 8 take away 6, that's 2. 15 take away 10, that's 5. The smallest one is the 0, so 0 goes here. Here is our completed activity network. For part B of the question, each activity requires one worker and the project must be completed in the shortest possible time, using as few workers as possible. We have to calculate a lower bound for the number of workers needed to complete the project in the shortest possible time. You must show your working. The first thing we need to do is find the total weight. We can do this by adding the weights of A, B, C, D, etc. up to M. And if we do that, adding those together, we get the total weight is equal to 71. Now the minimum completion time is 22. So what we now need to do is work out 71 divided by 22, and if we work this out, 71 divided by 22, it turns out we get 3.22, etc. And therefore, with this lower bound, we can conclude we require 4 workers. Now, for part C of the question, we have to schedule the activities using grid 1 in the answer book. Now, first of all, you can see here we've got our critical path A, E, H, J. They have 0 float. So the critical path is A, E, H, J. What I have shown in this table is the activities, the duration of those activities, the immediately preceding activities, and the floats of those activities. A, B and C, if I go back to the diagram, depend on nothing. D and E, if we take a look at those depend on A completing only. Then F, that depends on E completing, and it depends on B completing. And if I take a look at G, G depends on D completing. Through this dummy, it's implied that it also depends on B completing and E completing. If I take a look at H, that depends on E completing and B completing. I, in a similar way, depends on E and B completing. J, that depends on G completing and H completing. And K, that depends on I completing, and through the dummy, it's implied that K also depends on F and C completing. And if I take a look at L, that depends on F and C completing, and M also depends on F and C completing. Now, this table can be used to help form a Gantt chart. Now, start off with the critical activities. We can do this in rough first. This would depend on, rather, if I show those, what you have to remember in this problem is our minimum completion time is 22 and we require 4 workers. So we've got A with a duration of 4, and then I have E with a duration of 4. I have H with a duration of 7, and then I have J also with a duration of 7. So here are the critical activities. Now, B and C depend on no activities. We've got 6 and 10 respectively. So here we've got B and C. That takes us up to 10. So that's C. If I take a look at the floats of those, we've got 2 and 5 respectively. So that means here I've got a float of 2, and here I've got a float of 5. So that's A, B, C, and completed. E, H, and J are completed. So if I take a look at D, that depends on A completing only. It's got a duration of 2, so we might as well stick the D over here. It's got a duration of 2, and the float of D we know is 3. So the float takes us up to here. Now, E is critical. If I take a look at F, that depends on B and E completing. So F can start here at 8, and it's got a duration of 5. So F, that's got a duration of 5. So that takes us up to 13. So this is F. And if I take a look at G, this has got a duration of 6. So F's got a duration of 6, and this depends on B, D, and E completing. So I can actually start G over here. And we know that G has a duration of 6. So if I add that on, this is where G could go. Now, the problem is with this current configuration, we know that J depends on H completing, so that's fine, but it also depends on G completing, so that means G needs to finish before J can start. So what I'm going to do is instead move those. So if I move those, what I'm saying is I want G to go over here instead, and that will take me up to 14 if I have G over here, because J needs to start after G and H are completed. And what depends on F? Well, K depends on F completing. No other critical activities depend on F. So I could put F after C, and F's got a duration of 5, so that takes us up to 15. So F could go here instead. Now let's add on those floats. We've got 2 for F as the float. So that goes over here. And then for G, we've got 1 as the float so far. Now we know I depends on B and D only, and it's got a duration of 2. So we could put I over here actually. So I could go over here, and it's got a duration of 2. K depends on I completing. It also depends on C completing and F completing. So we can put K straight after I. So K has a duration of 6. So that will take us up to 22. So K could go here. And that's using some of the float of I as well. We don't need to do anything with those. Now L depends on C and F completing, so L can actually go after here. We're at 15 so far. Add on the 7, that takes us up to 22. And M, that depends on C and F completing, so M would have to go here. And it's got a duration of 5, so that will take us up to 20. So M would go here. So this is our completed Gantt chart. Let's complete this neatly. So here is our completed Gantt chart. It's completed neatly. Shows that we've got a minimum time of 22 4 workers are required for this project. Question number 3. We've got table 1, which shows the shortest distances in miles between 8 towns A, B, C, D, E, F, G and H. For part A, we have to use Prim's algorithm, starting at A, to find the minimum spanning tree for this table of distances. You must clearly state the order in which you select the edges of your tree. So, for part A, we were told we need to start with A. So, we write a number 1 above column A, and then we delete all of the row A. Looking down column A, we look for the smallest entry. The smallest entry is this 22. So we have A, H, with a weight of 22. We now delete row H, and then we write a number 2 above column H, and then we look for the smallest entry down A and H. That will correspond to this 24. So we have A, B with a weight of 24. We now delete row B and then write a number 3 above column B. Looking down A, B and H, the smallest entry is the 27. So DH has a weight of 27. we now delete row D and then write a 4 above column D. Looking down A, B, D and H, the smallest entry is the 21. CD has weight 21. We delete row C and then write a 5 above column C. We now look down A, B, C, D and H. The smallest entry is the 26. EC has weight 26. We now delete row E and then write 6 above column E. Looking down A, B, C, D, E and H, the smallest entry is 29. GD has weight 29. We now delete row G and then assign a number 7 above column G. Looking down A, B, C, D, E, G and H, the smallest entry is 34. FE has a weight of 34. We now delete row F and then assign a number 8 above column F. We have used Prim's algorithm. Here is the order in which we select our edges. For part B of the question, we have to state the weight of the minimum spanning tree. The weight of the minimum spanning tree, we have 22 plus 24 plus 27 plus 21 plus 26 plus 29 plus the 34. And what we can see here then, the weight is equal to 183 miles. For part C of the question, Table 2 shows the distances in miles between town J and towns A, B, C, D, E, F, G and H. Pranav needs to visit all of the towns starting and finishing at J and wishes to minimize the total distance he travels. Starting at J, we have to use the nearest neighbour algorithm to obtain an upper bound for the length of Pranav's root. You must state your root and its length. Now, in the question booklet, we have a copy of Table 1 here. Now, we are told in the question we start at J. And if we start at J, the smallest entry will take us to F. So, if we delete this row, then what we have done here is start at J and then gone to F. That has a weight of 25. So we write down 25 here. Now we need to obtain an upper bound. So we are at F and we assign a number 1 down column F, and then we delete row F. And then, just looking down F, the smallest entry is 34 here. And that will take us to E. So, we write a number 2 above E and also delete row E. Just looking down E, the smallest entry corresponds to the 26, and that takes us to C. So we are now at C, so let's put a number 3 above it and also delete row C. Just looking down C, the smallest entry is 21, and that takes us to D. So, now that we are at D, let's put a number 4 above column D and delete row D. And now we look down D, the smallest entry is 27, and that takes us to H. So we write a number 5 above column H and then delete row H. Now that we are at H, we look for the smallest entry. The smallest entry is the 22, and that takes us to A. So we write a 6 above column A and then delete row A. Looking down A, the smallest entry is 24, and that takes us to B. So we assign a number 7 above column B and then delete row B. We now look down B for the smallest entry. That will be 39. And that takes us to G. So we assign a number 8 above column G and then we delete the rest of G. Now that we are at G, according to the nearest neighbour algorithm, we need to go back to J. So, looking back here, you can see from G to J, that's got a weight of 49. And that takes us back to J. So now when we come to state the upper bound, 25 plus 34 plus 26 plus 21 plus 27 plus 22 plus 24 plus 39 plus 49, that's 267. So the upper bound is equal to 267 miles. For part D of the question, starting by deleting J and all of its edges, we have to find a lower bound for the length of Pronov's root. Now we are told to delete J, and once we delete J, we then apply Prim's algorithm of what's left over. Now happily for us, we already applied Prim's algorithm. We did that in part A. We found the weight to be 183 miles. So for part D, for the lower bound, we have the 183, which we found from part A, and this was found using Prims. And then we need to add on the two shortest values from J. So what I need to add on here are the two smallest values. Those two smallest values are the 25 and the 27. So we add on 25 and 27. And if we work all of this out, it turns out we get 235 miles. Question number 4. Direct roads between 6 cities A, B, C, D, E and F are represented in figure 3. The weight on each arc is the time in minutes required to travel along the corresponding road. We see in figure 3 the total weight of the network is 1648. Floyd's algorithm is to be used to find the complete network of shortest times between the 6 cities. An initial route matrix is given in the answer book. For part A, we have to set up the initial time matrix. So here is the initial time matrix. We add in dashes here, A to A, B to B, C to C, D to D, E to E, and F to F cannot be calculated. Now, if we take a look at the network, to go from A to B, there's one way of getting there directly. It's 57. We add here. A to C, directly, that's 95. A to D, that's 150. And A to E, that's 63. A to F, that's 230. Now we'd have the same thing going down column A. We have 57, 95, 150, 63, and 230. Now if we take a look at going from B to C, that's 72. And then B to D, well, from B to D there's not a direct way of getting there, so instead we will put the infinity symbol here. B to E, there is a direct way of getting there, 132. And B to F, there's not a direct way of going from B to F, so we put an infinity symbol here. So down column B we would have 72, infinity, 132, infinity. Now C to D, there's a direct way of getting there, 289. C to E, that's 160. C to F, that's 125. Now down column C, we have 289, 160, 125. Now D to E, that's 84. And D to F, there's not a direct way of getting there, so we put the infinity symbol. So here we have 84 and the infinity symbol. E to F, we've got 191, and the 191 would also go here. Here is the initial time matrix provided for us is also the initial root matrix. For part B of the question, we have to perform the first iteration of Floyd's algorithm. You should show the time and root matrices after this iteration. So, the first thing we need to do is write down the dashes from A to A, B to B, C to C, etc. and the corresponding roots will also not change. So, with these inputted, with our first iteration, we need to consider the A column and the A row. So if I perhaps put a box around those, this will help keep track of what needs to stay the same with our first iteration. So, the values that are boxed need to remain the same. So, the values remain the same from the boxed column and row for the time matrix, and for the root matrix, the boxed row and column remain the same. So now let's perform the first iteration. For this entry, we compare 72 with the sum of 57 and 95. 72 is smaller, so it's not changing, which means the corresponding element here will also not change. If we take a look at what we have here, then we are comparing infinity with the sum of 57 and 150. Now 57 plus 150 is certainly smaller than infinity, so the element here will be 57 plus 150, which is 200. And 7, and what would go here is A. If we take a look at the element here, we compare 132 with the sum of 57 and 63. 57 plus 63, that's 120. That's smaller than the 132. So 120 goes here. The corresponding element here would change from E to A. If we consider what would go here, then we compare the infinity with the sum of 57 and 230. 57 plus 230 is smaller than infinity. So here we have 57 plus 230, which is 287. The F here would be changed to an A. Now for this element, we compare 72 with the sum of 95 plus 57. 72 is smaller, so 72 goes here, and the element here remains unchanged. We write down B over here. Now we compare the 289 with the sum of 95 plus 150. 95 plus 150 is smaller than 289. So the sum of 95 plus 150, that's 245. and so the element here changes from D to A. For the element over here, we compare 160 with the sum of 95 plus 63. 95 plus 63 is smaller than 160. The sum of 95 plus 63 is 158. And the E will change to an A. Now we compare the 125 with the sum of 95 and 230. The 125 is smaller, so that remains unchanged, and the F here will also remain unchanged. Now we compare infinity with 150 plus 57. 150 plus 57 is smaller than infinity, so the element here will change. 150 plus 57, that's 207. The B here will change to an A. Now we compare 289 with the sum of 150 plus 95. 150 plus 95 is smaller than 289. So 150 plus 95, that's 245. And the C here will change to an A. Now we compare the 84 with the sum of 150 and 63. 84 is definitely smaller, so this remains unchanged, and the element here will remain as E. Now we compare the infinity with the sum of 150 plus 230. 150 plus 230 is smaller than the infinity, so the element here will change to the sum of 150 plus 230, which is 380. And the F here will change to an A. Now we compare the 132 with the sum of 63 plus 57. 63 plus 57 is smaller than 132, so the element here changes to 63 plus 57, which is 120. And the B here changes to an A. Now we compare the 160 to the sum of 63 and 95. 63 plus 95 is less than 160, so the element here changes to 63 plus 95, which is 158. So the C here changes to an A. Now we compare the 84 with the sum of 63 and 150. 84 is certainly smaller, so this remains unchanged as 84, and the D here will remain unchanged. Now here we compare 191 with the sum of 63 and 230. 191 is smaller, so the 191 remains unchanged, and the F here will also remain unchanged. Now here we compare infinity with the sum of 230 and 57. 230 plus 57 is smaller than infinity, so here we have 230 plus 57, which is 287. So the B over here changes to an A. Now, here we compare the 125 with the sum of 95 and 230. 125 is smaller, so this remains unchanged, and the C over here will remain. Now, we compare the infinity with the sum of 230 and 150. 230 plus 150 is smaller than infinity, so this element will change to 230 plus 150, which is 380. And so the D over here will change to an A. Now here we compare the 191 with the sum of 230 and 63. 191 is smaller, so this remains unchanged, and the E will remain unchanged. What we have completed here is the first iteration. We have here our time matrix, we have here our root matrix. In blue, we see the elements which have not changed, and in red, we see the elements which have changed. The final time matrix after completion of Floyd's algorithm is shown below. A route is needed that minimizes the total time taken to traverse each road at least once. The route must start at B and finish at E. For part C, we have to use an appropriate algorithm to find the roads that will need to be traversed twice. You should make your method and working clear. If I take a look at the original network, let's state the order of each vertices. We've got 1, 2, 3, 4, 5 for A. We've got 1, 2, 3 for B. 1, 2, 3, 4, 5 for C. 3 for D. 5 for E. And 3 for F. These are our odd vertices. So let's just write those down. With the odd nodes, we have A, B, C, D, E, and F. Now, we are told in the question that the route must start at B and finish at E. So, we need to consider the pairings of nodes A, C, D, and F, given that the route must start at A and finish at E. So, let's write down all the possible pairings. If I have AC, then we can add on to this DF, and we need to find out what that is. We could also have A paired with D, and then add on to this C to F, and we'll work out what this is. And we could also have A paired with F, and then C paired with D. So, AC, if we work out what that is, from A to C, you can see the shortest distance is 95. So here we have 95, and then DF, that will be 275. Now, we also have AD, the shortest length of that is 147. And then CF, that's 125. And then AF, that's 220. And then CD, that's 242. So now let's add all these together. Here we get 370. Here we get 272. And here we get 462. So what you can see is this is the shortest route. So what we now need to do is repeat AD and CF. So we will repeat AD and CF now. If I take a look at A to D, the length of that we said was 147, and the way we can get there is to go via E. So with that information, AD can be re-expressed as AED. So here we have AED, and with that we can conclude we can repeat AE, DE and CF, where AD is AE and DE. Now, for part D, we have to write down the length of this route. Now we know that the total weight of the network is 1648. So when we come to state the length, we've got the 1648. And then we need to add on to this the 272, which is what we got by repeating AE, DE and CF. So the total length is equal to 1920 minutes, where the length is the length of the route. Question number 5. We've got a list of 10 numbers above which need to be sorted into descending order. And to do this, we need to use a quick sort to obtain the sorted list. You should show the result of each pass and identify your pivots clearly. So, here is our original list of numbers, and for part A we need to use a quick sort to sort this list of numbers. So, first thing we need to do is identify the pivot. Now we've got 10 entries. The middle one will be in between the 5th and the 6th, so we choose the 6th entry, and so we would circle the 18, indicating this is our pivot. Now, anything larger than the 18 goes to the left, anything smaller than the 18 goes to the right, and we retain the same order in which the numbers are written. 30 is larger than 18, 12 isn't, 5 isn't, 2 isn't, 23 is, 36 is, 10 isn't, 15 isn't, but 24 is. And then we write down the 18 and underline it, indicating we've already used this as a pivot, and then everything smaller than the 18 we write to the right. So we've got the 12, we've got the 5, we've got the 2, we've got the 10, the 15 as well. So this is our first pass complete. Now for the next pass, the 18 stays where it is, that's not going to go anywhere. We've got two sublists and we need to identify a pivot for each. Now this sublist would have 36 as a pivot, and this sublist would have 2 as a pivot. So this is the third pass complete. Now for the next pass, the 36, the 23, the 18, the 10 and the 2 are not going to change. We've already used them as pivots. We've got a sublist here, here, and this 5, although it's in between two pivots, there's nothing to compare it with. So we don't need to do anything with this 5. Now the pivot here will be 24. And the pivot here will be the 15. Now, anything larger than the 24 we put to the left, anything smaller than the 24 we put to the right. So 30 is larger than the 24, so 30 would go here, and then we've got the 24 here, and we underline this, indicating we've used this as a pivot. Here, anything larger than the 15 goes to the left, anything smaller than the 15 goes to the right. Now, 15 would go over here because 12 is smaller than the 15, and we underline this, indicating we've used this as a pivot. And the 12 would go here, and here is where the 5 would also go. So what you can see here then is we have completed the sort. We've put the original list of numbers in descending order. The 10 numbers are to be packed into bins of size n, where n is a positive integer. When the first fit bin packing algorithm is applied to the original list of 10 numbers, the following allocation is obtained. That's what we see here. Now, for part B, we have to explain why the value of the integer n must be either 44 or 45. So here you can see we've got our original list of numbers, and we will be using the algorithm to pack these into bins. So, if I take a look at the sorted allocation, we have this 30 which is placed into bin 1. So if I open up a new bin, call it bin 1, currently it's got a size of n, and then I place the 30 into this bin, so that will leave a space of n minus 30. So let's cross off this 30, indicating we've used it. Now, if I take a look at this 12, well, the 12 was also placed in bin 1, which means the 12 goes here, and the space remaining then in bin 1 will be n take away 30, take away the 12, which is n minus 42. So let's cross off the 12, indicating we've used it. Now the next item is the 5. If we take a look here, the 5 has been placed into bin 2. So, if I open up a new bin, bin 2 say, it's got a size of n. I place the 5 into bin 2, and the remaining space then will be n minus 5. Now if the 5 has been placed into bin 2, that means there wasn't enough space in bin 1 to place the 5 into it. So this will imply the space that was left over in bin 1, which is n minus 42, this must have been smaller than the 5 for the 5 to be placed into bin 2. Now if I solve this inequality, you can see n is less than 47, in which case n is less than or equal to 46. The reason for that, n is a whole number, it cannot include the 47, so the values of which n can have will be whole numbers up to 46. Now, the next item that we need to place into a bin is the 2. The 2 has been placed into bin 1. So, this 2 over here has been placed into bin number 1. So the 2 would go here, and the space remaining then will be n minus 42, take away another 2, so that's n minus 44. So let's cross off the 2, indicating we've used it. Now, if the 2 has been placed into bin 1, that means there was enough space to place the 2 into it. So, if there was enough space, that means n minus 42 must have been greater or equal than the 2 for us to place the 2 into it, from which we can conclude n is greater or equal to 44. Now, we need to sort the 23. The 23 has been placed into bin number 2. So, we place the 23 into bin number 2, and the remaining space then will be n minus 5, take away another 23. So that will be n minus 28. So, we cross the 23, indicating we've already used it. Now, we need to sort the 18. Now the 18 has been placed into a new bin, bin number 3. So, if I open up a new bin, bin 3 say, it's got space n, I place the 18 into bin 3, which means the remaining space is n minus 18. So let's cross off the 18, indicating we've used it up. Now, if the 18 has been placed into bin number 3, that means there was not enough space in bin number 2 to place 18 into it, which means that the n minus 28, which is the current space left in bin number 2, is less than the 18. There was not enough space to place the 18 into bin number 2, which is why the n minus 28, the current remaining space in bin 2, is less than the 18. And from this we can conclude n is less than 46. And if that's the case, then n must be less than or equal to 45, for reasons we described before. Now, n is greater or equal to 44 and n is less than or equal to 45. So therefore, from here you can see n is either equal to 44 or 45. And that's exactly what we wanted to show. Now, whilst we're here, we might as well finish the sorting algorithm. So if I take a look at the 36, it's been placed into bin number 4. So if I open up a new bin, bin 4 say, it's got a size of n, I place the 36 into it, so the remaining space is n minus 36. So let's cross off the 36 indicating we've used it. We now need to place the 10 somewhere. The 10 has been placed into bin number 2, so the 10 would go here, and the remaining space, n minus 28, take away another 10, that's n minus 38. So let's cross off the 10 indicating we've used it. We now need to place the 15 somewhere. The 15 has been placed into bin number 3, so 15 would go here, and the remaining space, n minus 18, take away another 15, that's n minus 33. So now we've used up the 15, we've now got to place the 24 somewhere. That's been placed into a new bin, bin number 5. So if I open up a new bin, bin 5, it's got space n, I place the 24 into it, the remaining space will be n minus 24. So let's cross off the 24, indicating we've used it. Now this is all we needed to do for part B. We've shown n is either equal to 44 or n is equal to 45. Now for part C, we have to use the first fit decreasing bin packing algorithm to determine how the numbers can be packed into bins of size 45. So for part C, we need to use the algorithm to pack these items into bins. Now, if we go back to the question, we have to use the first fit decreasing bin packing algorithm, which is why I used the ordered list, which I found using my answer from part A. So, the bin size is 45. If I open up a new bin, bin number 1 say, currently it's got space 45. I'm going to place the 36 into bin number 1, and the space remaining then will be 9. 45 take away 36 is 9. So let's cross off the 36 here. I now need to place the 30 somewhere. Well, there's not enough space in bin 1, so I need to open up a new bin, bin 2, and place the 30 into it. So, when I open up my new bin, it's got space 45. When I place the 30 into it, it will have space 15 remaining. So let's cross off the 30, indicating we've used it. Now, I need to place the 24. There's not enough space in bin 1, there's not enough space in bin 2, so I need to open up a new bin, bin 3. It's got space 45. I place the 24 into it, and if I do that, the remaining space will be 21. Now, I need to place the 23 somewhere. There's not enough space in bin 1, there's not enough space in bin 2, there's not enough space in bin 3, which means I need to open up a new bin. So it's got space 45 when I open it, and placing the 23 into bin 4 will leave a space of 22. Now, I need to place the 18 somewhere. There's not enough space in bin 1, there's not enough space in bin 2, however, there is enough space in bin 3. So I place the 18 into bin 3, and the remaining space will be 21 take away 18, which is 3. So we've used up the 18. Now, I need to place the 15 somewhere. There's not enough space in bin 1, however there is just about enough space in bin number 2. So I place the 15 in bin number 2, and if I do that, the remaining space will be 0. Now I need to place the 12 somewhere. There's not enough space in bin 1. There's no space left over in bin 2. There's not enough space left in bin 3. However, there is enough space in bin number 4. So I can place the 12 in bin number 4. The remaining space then will be 10. So let's cross off the 15. Now I need to place the 10 somewhere. There's not enough space in bin 1. There's not enough space in bin 2. There's not enough space in bin 3. However, there's just about enough space in bin number 4, so I can place the 10 here, and the remaining space will therefore be 0. There's no more space left over in bin number 4. Now, I need to place the 5 somewhere. There is enough space in bin number 1, so the 5 can go here, and the space left over then will be 4. 9 take away 5 is 4. Now I need to place the 2 somewhere. There is enough space in bin number 1, so the 2 can go here, and the remaining space will be 4 take away 2, which is 2. So we have packed the items into bins of size 45. Here is the resulting allocation. Question number 6. In figure 4, the weights on the arcs represent distances. For the first part of the question, we have to use Dijkstra's algorithm to find the shortest path from A to H, and then state the length of the shortest path from A to H. So, in our answer book, we need to start off with A, so the working value here is 0, and then the final value, because there's nothing to compare this with, the final value is 0. We assign a number 1 to its order of labelling. Now, we've got 0 plus the 32, which is 32. Then we've got 0 plus the 75, which is 75. 0 plus the 95, which is 95. And then we've got 0 plus the 16, which is 16. So comparing the 16, the 95, the 75 and the 32, the 16 is the smallest, which means the final value will be 16, and the order of labelling for C will be 2. Now, let's take a look at everything coming off C. We've got 16 plus 50, which is 66. We've got 16 plus 70, which is 86. We've got 16 plus 105, which is 121, and 16 plus 113, that's 129. Now, the smallest from 32, the 66, the 86, the 121 and the 129, that's the 32. So the final value for B is 32, and we give it an order of labelling 3. Now, taking a look at what comes off B, 32 plus 33 is 65. (32 plus 15 is 47. And there's nothing else coming off now. What we need to do is compare the 47, the 65, the 86, the 121 and the 129. The smallest one is the 47, so E will have a final value of 47 and an order of labelling 4. Now, let's take a look at what comes off E. We've got 47 plus the 17, which is 64. We've got 47 plus 30, which is 77. And that's all that comes off E. So now we need to compare the 64, the 77, the 121 and the 129. The smallest one is the 64, so D has a final value of 64, and it will have an order of labelling 5. So now let's take a look at what comes off D. We've got the 64 plus the 50, which is 114. And that's all we can do for now. So we need to see which is the smallest from 114, the 77 and the 129. The 77 is the smallest, so F has a final value of 77, and it's got an order of labelling 6. So now everything off F, we've got 77 plus 25, that will be 102. And then we've got 77 plus 41, which is 118. So now the smallest from the 102 and the 118 is the 102. So G has a final value of 102, and it will have an order of labelling of 7. Now 102 plus the 10, that's 112. So that means nothing else to compare with. H has a final value of 112, and it has an order of labelling 8. So this is the complete diagram. Now we have to state the shortest path from A to H. Well, essentially what we need to do here is work backwards. So we have 112, take away the 10 gives us the 102. So our final is H, and before that we would have had G, and then from G we need to go to F, because 102 take away 25 is 77. So before G we had F, and then here we are at 77, and if I take away the 30 I end up at E with 47. So I need to go this way. So before F I was at E, and then before E, 47 take away 15, that gets me to the 32. So that means before E I must have been at B, and 32 take away 32 is 0, which means before B I was at A. So we started here at A. So now when we come to state the length of the shortest path from A to H, that will indeed be 112. So we are considering this value here. Now, one application of Dijkstra's algorithm has order n squared, where n is the number of nodes in the network. A computer produces a table of shortest distances between any two different nodes by repeatedly applying Dijkstra's algorithm from each node of the network. It takes the computer 0.082 seconds to produce a table of shortest distances for a network of 10 nodes. We have to calculate approximately how long it will take in seconds for the computer to produce a table of shortest distances for a network with 200 nodes. You must give a reason for your answer. Now, here, for part B of the question, we are creating a table of shortest distances, so we need to apply Dijkstra's to each of the nodes in turn. In other words, if we apply Dijkstra's repeatedly to n nodes, this would imply that we've got n lots of n squared, which is n cubed. What we are saying here is one application of Dijkstra's is n squared, and we are doing Dijkstra's for every node in the network, so we are applying the algorithm n times. So the reason we've got n lots of n squared, which is n cubed, we are applying the algorithm n times. So we are applying the algorithm n times. So now when we come to find out the time, if we go back to the question, we've got 200 nodes. For 10 nodes it takes 0.082 seconds. So our factor here will be 200 over 10. And we need to cube this because the order is n cubed. Okay, so that's why we cube that, and then we multiply this by 0.082. So if I calculate what this is, we have 0.082 multiplied by 200 over 10 cubed. So we get 656 seconds. Now for part C, we have to explain why our answer to part B can only be an approximation. Well, the order of n cubed does not mean that the order is proportional to n cubed, which is the assumption to what we found in our answer to part B, but it merely means that the dominant term is of order n cubed. Question number 7. Figure 5 shows a partially completed activity network for a project that consists of 14 activities. We have to complete the precedence table in the answer book for the 8 activities in Figure 5. So, here is a copy of that. Now, A, B and C depend on nothing. So we can put dashed lines over there. Now, if I take a look at activity D, that depends on A completing only. So, A would go here. Now, if I take a look at E, E depends on A completing only, and it's the same thing for F, that depends on A completing only. So we have A over here and A over here. Now, if I take a look at G, what goes into here is the B and the F. So G depends on B and F only. And if I take a look at H, what's going inside to H, we've got C. Then we've got this dummy, which implies that H depends on B, and it also implies that H depends on F as well. So H will depend on B, C, and F. Now, for part B of the question, the precedence table for the remaining 6 activities is given in this table here. What we have to do is complete the activity network in the answer book for the project. Your completed activity network must contain only the minimum number of dummies. So, first of all, with dummies there are 2 conditions. The first condition, we have at most 1 activity between 2 events. The other condition, 2 or more activities depend on a common activity finishing, but also depend on activities that are not common in finishing. So we use a dummy when either of these conditions are satisfied. So if we go and take a look at the next activity, I and J both depend on D, E, G and H. Now D, E, G and H are all shown, and I depends on both of them, and so does J. So we've got I, which depends on all of these activities, like so, and so does J. But the problem is, you can see here that we need at most 1 activity between 2 events. So what we actually need here then is the dummy. So the dummy would go over here. So now that's satisfied. We've got K, which depends on E, G and H. So E, G and H, K depends on all of those. Then we have L, which depends on I, J and K. So I, J and K, L depends on all of those. So if I have L coming out over here, then J goes before L and so does K. Now the problem is over here, you can see that we require a dummy because we can have at most 1 activity between 2 events. So I certainly need a dummy here somewhere. So if I adapt my diagram, let's get rid of this. We know that L depends on K. Now if we have this situation where J and K finish here, we could have a dummy here, which would imply L depends on I, J and K finishing. So that's L. Now we also have M and N, which depend on J and K. So J and K should go before M and N. So we could have M here and N here. Now the thing is, over here we need a common finishing point. So if L goes over here, M can go over here, and you'd find that 2 or more activities depend on a common activity finishing, but also depend on activities that are not common in finishing, so we can't have this situation. So if I have N finishing here, we can have a dummy over here. So this is our required diagram. Now let's do all this neatly. So here is the completed activity network with our correct dummies. Now for part C, given that all 14 activities have the same duration, we have to explain why activity D cannot be critical. Now what I've done over here is created a quick network diagram, and what we're saying is that each activity has the same duration. So let's pretend that each activity has a duration of 5. Remember, dummies have a weight of 0. Let's attempt a forward pass and a backward pass. So if I start off here with 0, 0 plus 5 is 5, and then 5 plus 5 is 10. I'm going to compare that with something else, so I'll leave that alone for now. Here I've got 0 plus 5, which is 5, and I've also got 5 plus 5, which is 10. 10's bigger, so 10 would go here. And then here I've got 10 plus 0, which is 10. That's bigger than the 5. So 10 goes here. And then inside here I've got 10 plus 5, which is 15. Everywhere else I'd get 15 apart from here plus here. So 15 would go here. And then here we would have 15. Because I've got 15 plus 0, which is 15, which is bigger than the 5 plus the 5, which is 10. So straight away I can actually see that, well, we also need to do the backward pass as well before we do anything else. So here I've got 15 plus 5, which is 20. I've also got 20 going here. And then here I've got 20 plus 0 and 15 plus 5, which is 20. And then here I've got 25 from here, and here I've got 25 here, and therefore 25 here. So that's my forward pass, and for my backward pass, if I have 25 here, that means I've got 25 here, and then here I have 25 take away 5, which is 20. Well, here I'd definitely have 20. And then 20 take away 0 is 20. Everywhere else I'd get 20. And then 20 take away 5 is 15. Okay, then I've got 20 take away 5, which is 15. And then here I've got 20 take away 5, which is 15. $15 would also go here. And here I would have, if I work out what this one is, I need to work out this first. So 15 take away 5 is 10. And here 15 take away 5 is 10. But here 10 take away 5 is 5. And then could also have 10 here, and then here to get 0. So here I've created forward and backward passes, and if I take a look at the activity D, the float of it, so the float of D, that's equal to this 15, take away the duration, which is 5, take away the 5 over here. 15 take away 10 is 5. So the float of D is 5. So what we can see here then is this float is a non-zero value. So activity D is not critical. Question number 8. Susie is preparing for a triathlon event that is taking place next month. A triathlon involves 3 activities: swimming, cycling and running. Susie decides that in her training next week, she should maximize the total time spent cycling and running, train for at most 39 hours, and spend at least 40% of her time swimming, and spend a total of at least 28 hours of her time swimming and running. Susie needs to determine how long she should spend next week training for each activity. We have to let X represent the number of hours swimming, y represent the number of hours cycling, and z represent the number of hours running, we have to, for part A, formulate the information above as a linear programming problem. We have to state the objective and list the constraints as simplified inequalities with integer coefficients. So, for part A, we have a maximizing problem, and what we need to do is maximize p equals y plus z. The reason for that is we need to maximize the total time spent cycling and running. Cycling is y, running is z. Now, we have to maximize this objective subject to the following constraints. For the first one, we've got x plus y plus z being less than or equal to 39. The reason for that is we have to train for at most 39 hours. Next, we've got 2/5 of x plus y plus z being less than or equal to x. The reason for that is we have to spend at least 40%. 40% is the same as 2/5 of the time swimming. Now, we know that x is swimming, which is where that x comes from, and 40% of her time, so this is the total time, x plus y plus z, 40% of that is 2/5 of this, and so we've got at least 40% of her time swimming, so this is why 2/5 of x plus y plus z must be less than or equal to x, because it's at least 40%. And if I rearrange this so I've got integer coefficients, I can see minus 3x plus 2y plus 2z is less than or equal to 0. And I also have x plus z being greater or equal to 28, which I've called equation 4. That's because we spend a total of at least 28 hours of our time swimming and running. So these are our inequalities. This is our objective function. Now for part B, Susie decides to solve this linear programming problem by using the two-stage simplex method. We have to set up an initial tableau for solving this problem using the two-stage simplex method. As part of our solution, we must show how the constraints have been made into equations using slack variables, exactly one surplus variable and exactly one artificial variable, and the rows for the two objective functions are formed. So, for part B, we need to rewrite all of these as equations. Now, first of all, from equation 1, I can rewrite that. So I have p minus y minus z equals 0, which I'll call equation 5. Then, from equation 2, because I've got a less than or equal symbol, I can rewrite this as an equation x plus y plus z plus s1 equals 39. And from equation 3, because I've got a less than or equal to symbol, converting this inequality to an equation, I've got minus 3x plus 2y plus 2z plus s2 equals 0. I've called that equation 7. And from equation 4, noting this time I've got a greater than or equal symbol, I can say then x plus z minus s3 plus a1 is equal to 28. I've called that equation 8. Now, with the two-stage simplex, what we need to do first of all is let I equal minus a1. The reason for this, minimizing a1 is the same as maximizing minus a1, and we've got a maximizing problem. And with that being the case, replacing the a1 with minus I, we can see then from equation 8, we have x plus z minus s3 minus I equals 28, from which we can conclude I minus x minus z plus s3 is equal to minus 28, which I've called equation number 9. And with all these equations, we can fill in this table. We've got our basic variables shown here, and along the top, we've got x, y, and z, s1, s2, and s3, a1, and the value. So, if I take a look at my p equation, I've got p minus y minus z equals 0. So I've got 1p, 0x, minus 1y minus 1z, and then I've got 0s1, 0s2, 0s3, and 0a1. If we remember, this is all equal to 0. And if I take a look at my I equation, I've got 1i minus 1x, 0y minus 1z, and then I've got 1s3, this is equal to minus 28, so I've got zeros here, here, and here. And if I take a look at the other equations, well, let's take a look at equation 6. I've got x plus, I've got 1x, rather, plus 1y plus 1z plus 1s1 equals 39. So the zeros go over here. Then if I take a look at equation 7, I've got minus 3x, 2y, 2z, and 1s2. This is equal to 0. So let's fill in these with zeros. And if I take a look at equation 8, I've got 1x, 1z, and minus 1s3 and 1a1. This is equal to 28. And then I fill in the rest with zeros. And then for the basic variables, I would have s1 to begin with, s2, and a1, as we see here. So here is our completed table. Now, for the next part of the question, the following tableau T is obtained after one iteration of the second stage of the two-stage simplex method. And what we need to do here is obtain a suitable pivot for a second iteration. You must give reasons for your answer. Well, for part C, here is a copy of the table. Now, what you can see here is the negative entry is this minus 1. And so in our objective row, minus 1 is the most negative entry. So let's just clarify this. This minus 1 is the only negative in the objective row. And from that, we can see then that the pivot is from the Z column. Now, what we will do at this point is work out our theta values. We can't work out 11 divided by 0. That's undefined. We've got 62 divided by 5. If I work out what that is, that's equal to 12.4. So my theta value here is 12.4, and 28 divided by 1, that's 28. So, which is the smallest value? Well, you can see the 12.4 is the smallest value, which will imply that the 5 in the S2 row is the pivot. So the 5 in the S2 row will be our pivot. Now for part D of the question, starting from Tableau T, we have to solve the linear programming problem by performing one further iteration of the second stage of the two-stage simplex method. You should make your method clear by stating the row operations you use. So for part D, here is a copy of T. Now, we know already the 5 is our pivot from the S2 row Z column. What we will do to begin with is work out the row operations. Now, if I call this row 1, this row 2, this row 3, and this row 4, now when we come to figure out what we need to do for our row operations, if I take a look at the Z column, where my 5 is, I want that to transform to a 1, and I want zeros everywhere else. This is what I want. And if you start off like this, then figuring out the row operations becomes easier. So, for me to get a 1 here, I need to take my row 2 and divide that by 5. So what we'll do to begin with is label the new rows. Here, I've got row 5. Here, I would have row 6. Here, I have row 7. And here, I've got row 8. Now, the idea here is, once we have found out what row 6 is, we can determine what row 5, row 7, and row 8 are by adding and subtracting multiples of row 6. Now, row 6, that will equal 1/5 of row 2. This will ensure I get a 1 over here. Now, row 5, we need to add and subtract from row 1 multiples of row 6. So row 5 will equal, well, it's a 0 over here, so that's going to equal row 1 plus 0 lots of row 6. And if I take a look at row 7, I want a 0 over here, so I will begin with row 3, and then from this I will subtract one lot of row 6. And if I take a look at row 8, I'm at -1, I want that to be a 0, so I take row 4, and then I will add on to that one lot of row 6. Here are the row operations we need to carry out. Now, the pivot is in the Z column, so for my basic variable, the S2 row will now be increased to say Z instead. So because my pivot was in the Z, I have now increased the basic variable to a Z here. The rest remain as Y and X. So now if we perform the row operations, I take row 5, and then this is going to be the same as row 1, plus 0 lots of row 6. In other words, I just copy down row 1. So I have 0, 1, 0, 1, 0, and 1 and 11. For row 6, I need to divide each of these by 5. So I've got 0, 0, 1, and then here I would have minus 2/5. Then here I would have 1/5. And then here I would have minus 5 divided by 5, that's minus 1, and 62 divided by 5. Now, I take row 3 and then I subtract row 6. So, I've got 1 take away 0, which is 1. Then I've got 0 take away 0. Then I've got 1 take away 1, which is 0. Then I've got 0 take away minus 2/5, so that will be positive 2/5. And then I've got 0 minus 1/5, so that's minus 1/5. And then I've got minus 1 take away minus 1, which is 0. And then I've got 28 take away 62/5, which is 78/5. And then for row 8, we've got row 4 plus row 6, so here I've got 0 plus the 1. Rather, 0 plus the 0. Then I've got 0 plus the 0. And then here, let's double check this one. I've got minus 1 plus 1, which is 0. And then I've got 1 take away 2/5. Rather, 1 take away 2/5, which is 3/5. And then I've got 1 take away 1/5. Rather, what I've got here is 0 plus, because I've got plus row 6, so that's going to equal 1/5. And then I've got over here 1 plus minus 1, which is 0. And then I've got 11 plus 62/5, which is 117/5. So here is the completed table. Now, what I know then is I have found an optimal solution. The reason for that, if I take a look at the objective row, I have no negatives in it. So there's no negative values in the objective row. Now what we need to do in the question is find out how long we should spend swimming, cycling and running. So we should spend, well here, for the cycling, which is what y is, we should spend 11 hours doing that. So we have 11 hours cycling, and then for swimming, which is what x is, that's 78/5, which is 15.6. So we should spend 15.6 hours swimming, and then we've got for the Z, that's 62/5. So we should spend 12.4 hours running. So here we have solved our linear programming problem using the two-stage simplex.